All right, so we're going to start off with graphing our exponential functions, which again, it's not new. You've graphed exponential functions before. So here's our equation. If you need to do it without a calculator, which you may have to from time to time, remember, pick some x values. I like to always go around my 0, so -3 to 3 is generally the one I tend to pick. So then all you have to do is plug in whatever value in for x into our equation. So this would become 2 to the negative 3, which, what happens with the negative becomes positive. So 2 to the third would give us 8. 2 to the -2, 4. 2 to the -1, to the 0, 2 to the -1 would be 1/2, 2 to the -2 would be 1/4, and then 2 to the -3 would be 1/8. So you want to get yourself some points, and then we're going to plot the points on our graph over here. Maybe a second to finish graphing now. So you should have your curve, your arrows on both ends, label it with your equation. And with our exponential functions, there's always one other thing that you have to draw with it. Got to draw your asymptote line on there, which for this one would be your x-axis. Asymptote lines are always drawn as dotted lines. So we would have that horizontal asymptote at y = 0. So if you have that done, go ahead and do part B, which tells you to reflect the graph from part A over the y-axis. So go ahead and reflect your graph if you have it done over the y-axis. Does our asymptote change? Nope. Asymptote's going to stay exactly the same. So then, yeah, part C, the equation of our new graph that we just drew would be y = 2 to the positive x. When you reflect over your y-axis, you just take your x value and you make it a positive. So my original function there is what we would call a decay. And then the new one, funky way to write, would be growth. But we'll talk that a little bit more in our next set of notes when we do our word problems with growth and decay. So then characteristics of exponential graphs, again, going over some stuff from our last unit. Domain would be XCR. There's really no restrictions on your domain there. However, your range is always restricted because of that asymptote line. So for the two graphs that we just drew up above, our range would be simply greater than 0 because it'll never actually reach 0, even though, remember, those calculators are restricted. It'll look like it actually reaches 0, but it never actually does. Common point for all graphs, unless you've translated them, would be your y-intercept at 0, 1, because everything to the 0 power is always 1. B controls the steepness. The higher the B value, the steeper the graph. So this one was a B value of 2. So if you make it a B value of 4, your graph will be steeper. For B value of 10, your graph is going to be steeper. If it's a smaller number between 0 and 1, so if you make it like 1/2 or 1/3, it's not going to be as steep. Keeping in mind, if you have a negative exponent, the other way you could rewrite your equation would be 1 over that b value to the x power. So up here in our first example, this could be rewritten as 1/2 to the x. Because remember, those negative exponents create the fractions. So instead of 2 to the negative x, it could become 1/2 to the positive x. It's the other way of writing that. So if the negative is out in front, that's a reflection over the x-axis, whereas if it's in the exponent, that reflected it over our y. Horizontal asymptote, everything else is the same. If you add or subtract a number at the end, that's a vertical shift, so that's going to make it go up and down, so that makes your asymptote also change up and down with it. And your intercept would always be 1 and then plus or minus whatever that shift is. So if you shifted it up 3, you would do 1 plus 3. Your y-intercept would be at 4. So let's take a look at some on the back. We'll see how this plays apart. So just trying to recall some things from last unit. Our a value, what does that control? Stretch and shrink, yes. That controls the stretch and the shrink, also known as the steepness. That's another way we could have said it. X minus h controls what? Left, right, so our horizontal shift. The k at the end, what does that control? Up, down, so our vertical shift. If the x is made negative, what does that reflect over? The y. And then if the y is made negative, that reflects over x-axis. So again, same rules as what we did last time. Nothing has changed except for the type of function we're going to be looking at. We're just now going to look at our exponential functions for it. So if we look at number 1 there, we have f of x equals 3 to the x, where g of x equals 3 to the x minus 4. So what shift is going to end up happening to it? Down 4. So of our original one, which would be our parent function in this scenario, our f of x equals 3 to the x power, our domain would be everything, so x is an element of the reals. What would our range for that one be? So y would be greater than 0, because it would be everything above the 0. Our y-intercept would be at the point 0, 1, because if I plugged in a 0 for x, I would get a 1. And our horizontal asymptote would be at y equals 0. So then our transformation would not change our domain. Our domain would still be x as an element of the reals. It could be everything. It does change our range, though. It makes our range move down 4. So instead of being greater than 0, y would be greater than negative 4. Everything just moves down the 4 units. Our y-intercept, though, it was at 1. So move 1 down 4, our y-intercept would be at 0, negative 3. And then your horizontal asymptote, that moves down 4 units also, so that would be at y equals negative 4. So a vertical shift affects those 3 things, your range, your y-intercept, and your horizontal asymptote. So looking at the second one, we got our graph there, f of x equals 1/2 x. G of x, though, is 1/2 to the negative x, so what would happen? What's our transformation? Reflection over the y. So then how could we rewrite that? Instead of 1/2 to the negative x, Jess? 2 to the x. So g of x would equal 2 to the x. That negative exponent would make your fraction flip, so it'd become 2 over 1, but we don't have to write the over 1. Let's take a look at our third one there. What's our transformation this time? Reflection over the x-axis. So again, parent function, the f of x equals 4 to the x. Domain would be everything. Range would be greater than 0. Y-intercept is at 0, 1. Horizontal asymptote is at y equals 0, because again, it's one of the parent functions for an exponential. So looking at the other one, if I reflect it over the x-axis, will our domain change at all? No, domain would still be everything. Our range, however, would change. Because if I reflect it over the x, that means it's going down. So my range this time would be y is less than 0. Because I flipped it and it's going upside down now. So my y-intercept then would become at 0, negative 1. Because again, it would flip down. But would our asymptote change? No, still going to be at 0. So then our last thing for today is the natural exponential function. So there is an irrational number that was coined the number e. That arises naturally in a variety of phenomena and plays a central role in mathematical descriptions of the universe. It kind of deals with the growth without bounds concept. It is often used in population kinds of questions. It's used a lot in finance kind of questions. It was this number e. So this guy named Euler, and I know it doesn't look like you would say his name that way, but that's actually how you say his name. He invented the number. Well, he didn't invent it. He found the number. It just existed there. He realized it existed there. He found it for the first time. So it became the number e because he's the one who found it. It is approximately 2.71. Those are the decimals we generally use for it. It can be found on your calculator also. There is a button on your calculator that's ln. So right here above the ln button, there is your e to the x. That is our number that we use. So if you hit the second button, and then you hit the ln, it brings up the e, and it always puts it as an exponent. So if you just want the normal e, you would put the exponent as 1. You just want e to the first power. So there's the number, 2.7182818828. It's not the same e. It's not the same e. So that's what the number is. It just naturally exists above the ln button. So go ahead, practice evaluating this one. So type in e to the negative third, and then write your decimal that you get. We'll go to the nearest 10,000, so 4 numbers after. So 0.0498. That second one, we don't need to type that in. What's e to the 0? Everything is 1. So e to the 1/6. So 1.1814. And then 2.7 times e to the 0.43. That's a 0.43 in the decimal up there in the exponent there. So 4.1506. So then you can also evaluate with it. Find f of 7, so just like all the other ones, we would just plug 7 in. So 25.1216. There you go. So now, let's take a look at what the graph of e to the x would look like. So go to your y equals. I already have stuff in there, so I'm going to clear that out. E to the x. And what does it look like? Looks exactly like what we were just graphing, doesn't it? It's an exponential function. It's just another kind of exponential function. So what graph does it look like in exponential? Which makes sense because your x is still in the exponent spot, so it's still an exponential function even though it's on a base of e as opposed to a number. So what quadrant does it lie in? It lies in 2 of them. It lies in quadrants 1 and 2. So what's its domain? X is now one of the reals. What's its range? Y is greater than 0. Our y-intercept? Still 0, 1. Horizontal asymptote? Still at y equals 0. So it's all the same exact properties as our other exponential functions, even though it represents a decimal. So go ahead and draw the graph of that. You got some table. You got the table in there. You just estimate your decimal. 7.3. So number 2 there, what is our transformation that's happening? It would go up 4. So then my graph, all I'm going to do is I'm just going to move everything up 4. So my f of x is the pink one there. My asymptote goes up 4. My y-intercept goes up 4. Each point goes up 4. You don't even really need to type it in the calculator. You just shift everything up 4. And then which way would that second one go? Yeah. So you got to flip it over the y-axis and then go down 3. Which I always move my asymptote first and then my y-intercept first. Because if I flip my y-intercept over the y-axis, it's in the same exact spot. So then I just move it down 3.